Good morning, students. So it's time to bring our journey of immunology to a very interesting point, especially in the context of the infectious environment, the ecosystem with teeming pathogens that we deal with. Immunity is one aspect of dealing with it. Immunodeficiency is a very clinically relevant condition where we fail to deal with it effectively. So the topic is, as you can see, AIDS and other immunodeficiencies. So like any multi-component system, the immune system is subject to failures. When it loses its sense of self and begins to attack the host's own antigens or own cells, we call it autoimmunity. And simply the presence of autoreactive cells is autoimmunity, but if it also results in tissue injury, then we call them autoimmune diseases, right? And when the system errs by failing to protect the host from disease, so the reverse process, okay, the opposite process rather. So instead of recognizing self antigens, now it is not even recognizing the foreign antigens. So it fails to protect the host from disease causing agents. We call it immunodeficiency. So the learning objectives at the end of this session are that each of you should be able to list which opportunistic infections are common in T cell, B cell, and innate system deficiency. Define what are primary and secondary immunodeficiency and list some important causes of each. And then we will take a journey to a very relevant and very, what do we call it, mercurial element of the immunology, of clinical immunology, that is the human immunodeficiency virus and its related acquired immunodeficiency syndrome. So we will study the stages of the HIV virus life cycle, that you should be able to tell the stages. Then you should be able to describe the effects of HIV on the immune system. So how the HIV affects immune system. You should be able to describe the phases of the HIV illness in an infected individual. And then illustrate at which sites do the HIV drugs act, the anti-HIV drugs. Okay. So immunity, as we discussed, is very intrinsic to life, and it's an important weapon in our war against pathogenic microorganisms. So if the immune system is deficient, it's like going to war without weapons. So the medic who fought a war without weapon, so who is it? So right now, as we can see, many of our government doctors fighting the coronavirus epidemic without the proper weapons. Which are the weapons we need in this COVID pandemic? The PPE, the so-called personal protective equipment. So we are lacking those equipment. This particular diagram, though, the cartoon is of Desmond Doss. So he was one of the American physicians who participated in the World War, even though he conscientiously objected to it. So he was a conscientious objector, but he played a very important role. When he saw the war was going on, he participated in it, and he won a Congressional Medal of Honor for his work over there. So basically, he didn't fight as a he objected to being enlisted for fighting as a soldier. Rather, he went to offer his services as a doctor. So the immunodeficiency diseases are divided into primary and secondary. So like we said, immunodeficiency is going to war without the weapons. So primary is when you never had those weapons. So it results from a genetic or developmental defect, which is present at birth, although it may manifest later in life. Whereas secondary is that you had those weapons, but you had them taken away at some point in time. So it is the loss of immune function. So it's not that it wasn't there, but you lost those powers. You lost your superpowers. Okay, Spider-Man became an average, the normal, Peter Parker. So Spider-Man became Peter Parker. So loss of immune function that results from exposure to an external agent. The external agents may be drugs, radiation, malnutrition, or infection. The most well-known, the most famous among which is HIV/AIDS. So again, the same thing. The primary immunodeficiencies result from genetic mutations. So disease-carrying genes are either inherited or there is some mutation taking place in the zygote. and the child is born with the various immune disorders. We will be discussing SCID, or the severe combined immunodeficiency, but there are other primary immunodeficiencies as well. Secondary, on the other hand, is because of external agents like IV drug abuse or malnutrition, chronic diseases like diabetes. So we say that chronic people who are chronic, like this time it is being said that people having comorbidities like diabetes, hypertension, heart disease, respiratory disease are more vulnerable to the coronavirus disease, right? More vulnerable to the severity of the coronavirus disease, and they are more likely to require intensive care, or more likely to require ventilatory support, more likely to die, of course. So some form of immunodeficiency results because of chronic diseases or drugs. All of this plus HIV and AIDS, so all of that is part of the secondary spectrum. So primary immunodeficiency, now, like I said, when you never had your weapons. So they were because of some genetic defect. So that genetic defect could involve a gene of the innate system, of the adaptive system. Adaptive also, it could involve the humoral and cell mediated separately, or it may involve them in a combined fashion. So any of these genes may be defective, any gene, okay? So in 50% of the cases, we see it is the B cell defects. In 10% it is T cell defects. In 20% it is combined B and T cell defects. So 80% is adaptive immunity. The remaining 20% is innate immunity. Among innate immunity lie mostly the cells or the molecule cells like neutrophils, macrophages, which are phagocytes, or the molecules like complement. So the genetic defect may lie in any of these areas. So this is a well-known classification of innate and adaptive. Innate having cells and molecules like complement, cells like phagocytes. Adaptive having the humoral and the cellular. Humoral deals with, so humoral or the B cell mediated immunity deals with extracellular microbes, extracellular antigens. Innate deals with various pathogens non-specifically. Adaptive deals in a specific and an antigen specific fashion. That is the basic difference. Adaptive consists of lymphocytes and their products. Humoral consists of B lymphocytes, cellular consists of T lymphocytes. Humoral acts through antibodies, cellular acts either directly through cells or through cytokines. Humoral responds to extracellular microbes, extracellular antigens. Cellular responds to intracellular microbes, intracellular antigens. Could be either phagocytosed by the antigen presenting cell, or could be presented by the other infected cells like virus infected cells, cancer cells. These are the various cells involved in the adaptive immunity. We already saw it in the previous slide. So phagocytes, granulocytes, phagocytes meaning monocytes, macrophages, neutrophils, and even the other ones like mast cells, dendritic cells. So all of these are part of the non-specific immune system. B cells and T cells for the specific, for the adaptive immune system, antigen specific system. So now, which are the pathogens that they fight? Okay, so this is important because for the first objective that we saw which opportunistic infections are common in these deficiencies. So you will know that only when you know what do they fight. So like we already said, the humoral immunity fights extracellular pathogens. So primarily it means the encapsulated organisms. Okay, so organisms like pneumococci, so streptococcus pneumonia or pneumococcus, which typically causes your pneumonia. Okay, then there is meningococcus, Neisseria meningitidis. So that typically causes meningitis. And there is H influenza. Okay, H flu, that is wrong. It's H influenza, Haemophilus influenza. So all these capsulated organisms, the B cell immunity classically protects against them. How? The antibodies coat the surface of the capsulated organisms and function as opsonins. That is, they help opsonization, help phagocytosis. So in absence of your B cell, in a defect of B cell immunity, your immunity is lost or is weakened against these capsulated organisms. So many times we have to protect by giving vaccines against these. Classic example being when autosplenectomy happens. Have you heard of the term autosplenectomy? So a patient of sickle cell disease gradually loses his spleen, okay, when they grow up, because they have these vaso-occlusive crisis. Sickle cell disease mein kya hota hai? Your RBCs, they undergo sickling, And when they undergo sickling, they can result in microvascular obstruction and the patient presents in crisis, various crisis. कभी bone pain लेके आता है, कभी abdominal pain लेके आता है. Okay, so all those kind of presentation, clinical presentations are there. The spleen initial days it is enlarged because there is basically what is happening in sickle cell disease is that the RBCs, the hemoglobin is polymerizing, RBCs are sickling, and those sickled or the misshaped RBCs are being removed by the spleen. So extra vascular hemolysis ho raha hota hai. So initially the spleen is enlarged, but later in the course of the disease, because of the vaso-occlusive constant obstruction, the spleen undergoes infarction. Okay, small infarcts leading gradually to bigger infarcts, leading gradually to the spleen being reduced to a fibrous nubbin. So the spleen is lost completely. So that is known as autosplenectomy. In those cases, typically those sickle cell disease patients have to be protected by vaccinating them against pneumococcus, meningococcus, H. influenzae, the capsulated organisms. Okay, and Giardia lamblia. So this is one of the parasites that we know of. So just remember that humoral immunity is important for capsulated organisms. What is cellular immunity important against? So cellular deals with intracellular pathogens, right? So classical example of an intracellular parasite or intracellular pathogen is, which we discussed already, the infected cells. Infected with what? Viruses, right? So virus, like for example, the coronavirus disease. So that is going to enter the respiratory epithelial cell and it is going to take over or hijack the genome. It is going to produce its own, it is going to use it as a factory to produce its own kind, to reproduce, you can say. So those cells now are like, have to be killed, have to be destroyed in order to destroy the virus. So that is one form of protection that the cellular immunity offers. So if your cellular immunity is weak, okay, so then you are more prone to infection by viruses. Similarly, fungi like Candida, Aspergillus. So candidal ulcers in the mouth, candidal ulcers in the vagina. So these are the commonest manifestations that a patient of HIV presents with. Okay. So HIV results in which cell destruction? Are you aware of how HIV acts? We will be seeing it in greater detail later, but basically just remember that T cell, it is the T cell limb of the adaptive immunity that is lost because of HIV. And of course, T cell, when T cell is lost, it is also going to impact your B cells. We'll see how. But if you just consider the T cell, you will lose your immunity to viruses. So they are more prone to developing various viral pneumonias. So even HIV patients have to be protected now in this COVID pandemic. Then they are going to be vulnerable to fungi. So like I said, candidal ulcers of the mouth, candidal ulcers of the vagina, known as, and then Aspergillus infections. So all of these fungal infections are common in T cell disease. Protozoa. So protozoa or multicellular parasites. So these are multicellular parasites. Even the fungi. Okay, fine. So these protozoal, so Pneumocystis carinii, for example, Pneumocystis carinii disease is the most, again, one of the common pneumonias, common types of pneumonia witnessed in HIV. And then bacteria. So which is this bacteria? Are you aware of this bacteria? So this Mycobacterium is nothing but the bacteria that causes tuberculosis and the bacteria that causes leprosy. So Mycobacterium tuberculosis and Mycobacterium leprae. So these are classically those bacteria which can escape your B cell response, which can fail to be killed by antibodies alone. So they enter the cells, or even if they are taken up by macrophages, okay, they enter the like macro. See, generally all the bacteria will be countered by both T cell and B cell. Okay, you remember the T dependent antigens and T independent antigens. So peptide antigens all being T dependent, the B cell is going to need T cell help to fight them. But here what happens is that the macrophage ingests this bacteria, Mycobacterium, tries to present it to the T cell, but many a times the T cell will not respond effectively and the bacteria keeps multiplying inside the macrophage. It forms bundles known as cigar bundles. So under the microscope, you see them as cigar bundle appearance. So a lot of mycobacteria, a lot of bacilli will be bundled up together. So like a bundle of Cuban or Hawaiian cigars. Okay, so they are bundled together. So so unless your T cell, meaning normally the T cell will fight them. So like for us, for the immune people, tuberculosis is very ubiquitous in our environment. Okay, when you walk through the hospital, you are exposed to TB bacilli, you are exposed to TB, but you never get TB. That is because your T cells are strong enough to fight them. But in case of HIV, when the T cell is destroyed, Mycobacterium tuberculosis is the commonest secondary infection that they come up. The serious infection like Candida ulcers are not so serious, but tuberculosis can be very serious. In fact, tuberculosis, US people had never seen tuberculosis, had stopped seeing tuberculosis for a long time. But with HIV epidemic, they started seeing tuberculosis once again. So see, here the viruses basically are tackled by the CD8 cells. CD8 cells directly recognize the MHC1 peptide complex. They don't need the antigen present in cell, the phagocytes. So viruses are not fungi are, so are the bacteria. Just remember it. So viruses are here, protozoa are here, but here the fungi and bacteria. Complement again, fourth. Okay, complement, one of the complement components, C3b. You remember that? C3b is also a very effective opsonate. So it opsonizes the capsulated organism, which pathogens they tackle normally. So then accordingly we have the disorders. So some disorders, one of which we'll study, severe combined immunodeficiency. Combined because it affects both limbs of the adaptive immunity. Okay, it is a T cell disorder, but it is also going to affect B cell response, because your T independent antigens, even the B cell requires T cell help for the T dependent antigens, thymus dependent antigens. The B cell requires T cell help. The T helper cell, is going to activate the B lymphocyte to become plasma cell to secrete antibodies. So severe combined immunodeficiency is not only a defect of the T cell, it is also indirectly a defect of the B cell. Then there are others like Wiskott-Aldrich syndrome. DiGeorge is when the thymus fails to develop at all. Okay. Just remember that most of the T cell disorders will lead to B cell impairment. And then there are B cell defects like X-linked A gamma globulinemia or selective immunoglobulin deficiency. So, there is some defect in the enzymes required for the class switching, the isotype switching or the class switching, which is required after the T helper cell activates the B cell and the B cell becomes a plasma cell. It undergoes class switching so that it starts secreting IgG, A, and E. Initially, it is only expressing IgM and IgD. So in order to secrete IgG, A, E, it has to undergo class switching. So if that class switching fails, then there can be defect of this. So IgA deficiency. These patients, what they will present with? So if there is I'm sorry, I cannot write anything, so I'm just speaking. So take note of it. So if IgA deficiency is there, IgA is important where? It is important as a secretory antibody, right? It is a secreted antibody. It is important in the mucosal linings. It is important in the gastrointestinal tract. It is important in the respiratory tract. So it will lead to respiratory infections, pneumonia, recurrent pneumonia, and all. So recurrent respiratory infections can result from IgA deficiency. And then A gamma globulin. So okay, we'll just look at the Hyper-IgM, X-linked Hyper-IgM syndrome. We'll look at that. Okay. Phagocyte disorders, chronic granulomatous disease, leukocyte adhesion defect. So we'll be covering those. You don't need to go into the details of this. Okay, your learning objectives include HIV, but I thought that it's better to discuss some of the primary immunodeficiencies before proceeding to secondary ones. So chronic. So these basically what they'll do. They will either not allow the phagocyte to reach the site, like leukocyte adhesion defect will not allow the phagocyte to migrate to the site of inflammation. Chronic granulomatous disease will not allow the phagocyte to do the killing. So even if it reaches and it phagocytoses, still it is not able to do the killing. So these are the phagocyte disorders. Complement disorders, I'm not covering them in detail, but you just remember that even the complement system can have abnormalities. So here are the opportunistic infections. I have not defined it anywhere. So look up the definition. But what can you think? What is an opportunistic infection? So it is that infection which will normally not present in an immunocompetent individual. But if for some reason the component of the immune system is deficient, then those infections which are normally easily fought off start appearing. Okay. So these are the opportunistic infections that appear in T cell disorders. The previous slide, okay, it's the replica of the previous slide. I told you the T cell disorder, T cells are required to fight viruses, fungi, parasites, and protozoa, and mycobacterium. So those disorders. If there are B cell defects, then the opportunistic infections will be bacterial infections. Especially which ones did I mention? We saw in the previous slide, antibodies are important for fighting capsulated bacteria like pneumococcus, meningococcus, Haemophilus influenzae. We discussed about autosplenectomy in sickle cell disease and the requirement for immunization against capsulated organisms. So these are the opportunistic infections. In disorders of phagocytes, that is neutrophil, macrophage function. So we discussed in the previous slide, they will lead to fungal and bacterial infections. So again, they are important for phagocytosing, they are important for presenting it. For viruses, the CD8 toxic cytotoxic cell does not require antigen presenting cell. So just remember that viruses are not part of this spectrum, but the CD4 T helper cell requires the antigen presenting cell. So they will result in this. And then the complement disorders, again, I said complements are important as opsonizing factors. So they will lead to bacterial infections, especially capsulated organisms. So this is the hematopoietic cell cycle, which you must have studied in physiology. The stem cell giving rise to the myeloid progenitor and the lymphoid progenitor. The myeloid progenitor giving rise to your granulocytes and the monocytes, neutrophil monocytes. So these are your phagocytes of the innate immune system. So this is your innate limb, okay? And the lymphoid progenitor, of course, this is the forerunner of the adaptive immune system. So adaptive is nothing but lymphocytes and their products. So it will give rise to your B cell precursor and the T cell precursor, and then it will mature into a mature B cell or a mature T cell. And of course, when they get activated, they become effector cells and memory cells, like that, so on and so forth. So at each step, there can be a defect. So if the defect lies right here, it is known as reticular dysgenesis, can have a global impact on the immune system. Similarly, if there is a defect here, it is congenital agranulocytosis. So there is a complete absence of granulocytes. Here, the granulocytes have been produced, monocytes have been produced, but these granulocytes or neutrophils are chronic granulomatous disease. So they are unable to do the killing. So they are also phagocytosing. You can see those blue dots, but they're not doing the killing. Okay, leukocyte adhesion deficiency, like I said, they have been produced, but they cannot migrate, they cannot reach the site of inflammation. Coming to this side, if the defect lies here at the lymphoid progenitor level, severe combined immunodeficiency. So at this level, it is severe combined immunodeficiency. But like I said, even if it affects the T cell, it can lead to combined immunodeficiency. So you can see here that if the pre-T cell cannot develop into a mature T cell, so this is this part is happening in the bone marrow. ये bone marrow शुरू का development bone marrow में होता है, B cell का भी T cell का भी, बाद में T cell precursor migrate करता है thymus में. So the rest of the maturation takes place in the thymus for the T cell, but for B cell it happens in the bone marrow. Now if thymus is absent, DJOG syndrome. So again, your T cell will not develop. T cell will not develop. It will also impact your B cell. So mature T cell has an impact on the development of mature B cell also. So it is also combined immunodeficiency. So here also it's combined. Here also it's combined. Then there is another syndrome known as Bayer lymphocytes. DJOG syndrome also combined. Bayer lymphocyte syndrome, where there is a defect in the MHC proteins. So the antigen cannot be presented. So it's a Bayer lymphocyte syndrome with lacking MHCs. MHC is a very critical component of the immune system. So if MHC is not there, it's bare. Okay, ganja hai, does not have hair on the surface. So Bayer lymphocyte syndrome, it's not called combined immunodeficiency, but it is also similar to that. Wiskott-Aldrich syndrome is also defect of some CD molecule on the T cell. And you can see the X-linked A gamma globulinemia. So if the pre-B cell does not mature into a B cell, A gamma globulinemia. So no antibodies will be produced. Precursor B cells will be there, but no mature B cell. Basically, the heavy chain gene rearrangement happens, but the light chain gene rearrangement fails to happen. So it stops there. So, and then if the mature cell has been formed, that is each B lymphocyte expressing a unique IgM and IgD on its surface. So the Ig gene rearrangements have happened successfully. So the B cell is mature, but now on encountering the antigen, it has to get activated into a plasma cell. So that is not happening. Either it is common variable hypogammaglobulinemia, that is Ig levels will be very low, X-linked IgM syndrome. So like IgM it is secreting, but the class switching is totally failing. So it cannot secrete IgG, IgA, IgE like that. Selective immunoglobulin deficiency. So class switching is affected, but not totally. So maybe it is not secreting IgA. The rest it is secreting IgG, IgE, IgM. Of course, it will secrete. So lymphoid lineage affects the adaptive immunity. Could affect both T and B cells. Could affect B cell alone. So just remember that if B cells are affected, they are वो अकेले है. But if T cells are affected, then वो दोनों को लेके डूबेगा. खुद तो डूबेगा ही, दूसरे को भी लेके डूबेगा. तो T cell plus B cell, that is combined immunodeficiency. If the myeloid lineage is affected, it is representing the innate immunity. It will affect the phagocytic function. So let's start with the T cell defect, that is severe combined immunodeficiency. It is a group of rare primary immunodeficiencies. PIDs, I just abbreviated the primary immunodeficiencies. So there is a profound block in T cell development. So we saw in the previous picture that it could lie at the level of T cell precursor, it could lie at the level of lymphoid progenitor, or it could lie even later. So complete absence of T cells, but because T cells are required for B cell response, where they are required? In the activation of B cells, in the formation of plasma cell and the production of antibodies in class switching. So all of these will be affected for B cell also. So both limbs of the adaptive immunity are affected. So some of the molecular defects that have been observed, okay, there are many, but I'm just listing some of them. So if there are recombination activating genes, okay, RAG1, RAG2, that is defective, there will be no T cell receptor, there will be no immunoglobulin B cell receptor, nothing will be there. So both are affected, severe combined immunodeficiency. If there is a defect in JAK3, so JAK3 and interleukin 2 receptor. What is interleukin 2? So when the T cell first gets activated, there are two signals. One is the T cell receptor signal, one is the co-stimulatory signal. So when signal 1 and signal 2 are both present, then they will activate the interleukin 2 production. IL-2 secrete hoga, IL-2 receptor bhi aayega. Autocrine signaling se the first proliferation of T cell will happen, and T cell will give rise to memory cell, effector T cell, and then that effector T cell can interact with the B cell and activate the B cell also, okay, through CD40 ligands. That will be the second signal for the B cell. So all that will depends on the interleukin 2 receptor. The T cell receptor to ban gaya, RAG1, RAG2 problem nahi hai. Receptor ban gaya, but if after receiving signal 1 and signal 2, the interleukin 2 autocrine stimulation fails because of defect in the receptor or because of defect in the signaling. JAK3 is one of the proteins involved in that IL-2 receptor signaling. The IL-2 will come and bind to its receptor. It will activate some proteins including JAK3. So that will lead to a defective signal from IL-2. Later, it can also, the same receptor gamma chain. The gamma chain is common for interleukin 2 receptor, interleukin 4 receptor, interleukin 7 receptor. So if that gamma chain mutation happens, it can affect signaling from all these. So it can affect, interleukin 4 is required for Th2 type of response, IgE production from B cells. So all of these, like 21 is required for your Th17 type of response. So all that defect can happen. ZAP70 is similar to this one because ZAP70 is a protein involved in the T cell receptor signaling. So पहला जो signal 1 आता है, T cell receptor बन गया है, but T cell receptor जब MHC peptide को encounter करेगा, there will be signal 1. That signal 1 requires one of the proteins involved in signal 1 is ZAP70. So if that is defective, again defective signal from T cell receptor. So all of these, many of these are affecting only the T cell, but you know why it is called combined, because it is indirectly going to affect B cell also. Bare lymphocyte syndrome, I told you that there is a defect in class 2 MHC gene promoter. So no class 2 MHC molecules will be formed. Viscodal-rich protein, it affects one of the protein in the T cells. So just remember that. ADA, and have you covered, I'm not sure you have covered, I think you have covered the nucleotide metabolism. So you must have encountered adenosine deaminase deficiency. So in absence of adenosine deaminase, what happens is that adenosine fails to get converted to inosine, and then the further purine catabolism to uric acid, so that fails. So inosine to hypoxanthine to whatever. So that particular pathway is obstructed. So now more and more of adenine keeps getting accumulated, and that affects your purine nucleotide and the purine nucleotide metabolism. That affects your DNA synthesis. So it has been particularly found to ideally DNA synthesis can be a global problem. So if DNA synthesis is affected, all fast dividing cells will be affected. But somehow we have found that ADA deficiency particularly manifests in your T cell dysfunction, in your lymphocyte uh, hematopoiesis hematopoiesis defect. So that leads to severe combined immunodeficiency. So in this, if this SCID is because of ADA deficiency, we can replenish the, we can give recombinant adenosine deaminase, or we can give gene for that. So gene therapy for adenosine deaminase can be given. Similarly, purine nucleoside phosphorylase. So that is also another enzyme involved in purine catabolism. So that deficiency also results in DNA defect. So toxic metabolite in the T and B cells accumulates, and that causes your SCID. So again, the same thing is presented in a diagrammatic form. So you have the T cell, and you have the T cell interacting with a antigen presenting cell here. This is a B cell, but I'm using it as both, as an antigen presenting cell also, because you know very well that B cell can be an antigen presenting cell also. So first thing is that the T cell receptor might not get formed itself because of RAG1 and 2 defect. दूसरा है कि बंद तो गया है, but there is a ZAP, so this signal 1, so ZAP70 defect. So RAG1 2 defect, ZAP70 defect, that is signaling is not happening. तीसरा है कि signal 1 आ गया, signal 2 आया यहाँ से, CD28 and B7 interacting, this is co-stimulation, signal 2. So they will lead to production of interleukin 2 and the interleukin 2 receptor, and that interleukin 2 will activate this T cell through autocrine signaling. But now if there is a defect in the interleukin 2 receptor, okay, or that same receptor gamma chain is also involved in interleukin 7 and all those things, so that defect will also lead to T cell defect and SCID. Or there is if the receptor is fine, but there is a defect in the downstream signaling, JAK3 is one of the proteins involved, deficiency in JAK3 pathway, so interleukin signaling molecule, that again is responsible for SCID. So all these. Now similarly, the similar impact it will have on B cells. What all impacts it will have? If the interleukin 2 gamma receptor chain is defective, that means interleukin 4 gamma chain, interleukin 7 gamma chain, I told you the gamma chain is shared between these receptors, so it is defective here also. So when you want your T helper cell to activate the B cell, Th2 response, Th1 response, Th17 response. So Th2 particularly uses interleukin 4 to activate it to produce IgE. So that won't happen. So वो नहीं होगा. Okay, so that is also one form of defect. Then X-linked A gamma globulinemia. This is another disease altogether. We're not discussing SCID. So this is a B cell defect. What happens? That when the antigen and so when your IgM interacts with the antigen, it delivers one signal, and signal 2 comes from your CD40 ligand interaction. So for the B cell now there are two signals. For T dependent antigens, it needs two signals. One comes from the antibody antigen binding, one comes from the CD40 interaction with CD40 ligand on an activated T helper. So both signals are necessary. For T independent antigen, only this signal is sufficient. So now we are saying that this signal itself, because Bruton's tyrosine kinase is one of the proteins involved in the signaling. So signal 1 deliver nahi ho pa raha hai, defect in Bruton's tyrosine kinase. This leads to X-linked A gamma globulinemia, because कुछ होगा ही नहीं, कोई भी immunoglobulin नहीं बनेगा. यहाँ पे major पहला signal ही defective है. Or second probability is that CD40, this particular signal is defective. Okay, so defect in CD40 ligand, this particular ligand is not there, so you will not, signal 1 to milega, signal 2 nahi milega. So this is known as X-linked Hyper-IgM syndrome. Hyper-IgM. Okay, we will cover this disease. Why? Because when signal 1 comes, IgM production can start. So it can start producing IgM. It can also start producing secreted IgM, secretory IgM, जो pentameric हम लोग बोलते हैं. यहाँ पे तो सब monomeric होता है. When it is secreted, then it becomes pentameric. So that it can do. But इसके बिना वो IG class switching नहीं होगा. So it cannot produce IgG, it cannot produce IgA and IgE. तो वो जो bivalent IgA secrete करता है या फिर IgG और IgE secrete करता है, that won't happen. Only IgM will be secreted. So that is one thing. Bare lymphocyte syndrome is when MHC itself is not. Also RAG gene, हाँ recombinant activation gene defect में ये भी affect होगा, ये भी affect होगा, दोनों affect होंगे जैसे interleukin 2 receptor defects, right? So I think this isn't too much detail, you don't need to remember it, but I only need you to understand it. So coming to SCID now, severe combined immunodeficiency. What are the opportunistic infections? So which opportunistic infections will be seen? I told you both T cell and B cell are being defective. So you will see a wide range of infections, and the infant will start having these infections at a very early stage of life, 3 to 6 months. Severe recurrent, like fungal infections, like protozoal infections, pneumocystis. Carinae को ही अब जीरो वेकी भी बोलते हैं. So pneumocystis carinae pneumonia या PCP is now called pneumocystis जीरोवेकी pneumonia. Prolonged diarrheal illnesses, severe bacterial, viral, all sort of infection basically. You can't, so life threat, even if you try giving them live viral vaccines like polio, measles, rotavirus. Okay, rotavirus is one of the most common, it is the most common diarrhea causing virus in children. That is why we say that in children you don't need to give antibiotics for diarrhea. Like in adults, we take metronidazole and ciprofloxacin if you have heard. But in children, we never give them because it is mostly not because of bacteria or amoeba. It is because of rotavirus. But in these children, you can't give these vaccines. You can't give a bacterial vaccine like BCG, which is live. So all these things can create problems. Initial 6 months, you know that the infants carry maternal antibodies obtained through placenta or obtained through breast milk. So the humoral immunity will be somehow covered for the first 6 months, but the cell-mediated immunity will be affected from the beginning. So when I'm saying 3 to 6 months, so you will start having candidiasis, you will start having this. So whichever things require antibodies, you can still be, the infant can still be protected, but when it requires lymphocytes, meaning T cells, that will not function. So oral fungal infections, lung infections like pneumonia, GI infections like diarrhea, failure to gain weight. Okay, so this is a very common thing in all pediatric disorders. You will find that failure to gain weight, also known as failure to thrive. Okay, so that is a common complaint that the mother will come with कि बच्चा वजन नहीं हो रहा है, बच्चा कमजोर है, बढ़ नहीं रहा है. So that is also one of the things that to look for. So there was a movie starring John Travolta known as The Boy in the Plastic Bubble. So in order to protect such a child, you need to provide them a totally sterile atmosphere. Okay, how will you do that? So any object including food has to be first sterilized, but extraordinary effort is needed because of course you're going to meet people, so direct contact with other person, your mother, your father, other person, and with unfiltered air. So even air, तो air से तो माँ बाप से भी नहीं मिलोगे, हवा से तो मिलना ही, ऑक्सीजन से तो मिलना ही है सबको. So the boy tried to live in a bubble. Okay, so there is also an episode of Seinfeld, if you watch sitcoms, in which George interacts with one bubble boy. Okay, more about that later. So that was T cell defect or combined T plus B cell defect. Now coming to only B cell defects. So the only disease that we'll look at is X-linked hyper-IgM syndrome. So I told you, so it's an X-linked disorder, and as I told you, the CD40 ligand is defective. So because of CD40 ligand defect, there is an impaired communication between T cells and B cells. So IgM antibodies will be present. It may even be higher than normal. Why? Because signal 1 coming from antibody antigen interaction is there, but low levels of other classes of antibodies. Why? Because the signal 2 coming from CD40 ligand interaction, CD40 on B cell, CD40 ligand on T cell, that is not there. There is impaired communication. So isotype switching or class switching, which is required for IgG-AE, is not there. Affected children suffer from recurrent respiratory infection. Why? Because IgA is required as a secretory antibody. The bivalent secreted form it plays a very important role in neutralizing the viruses, the bacteria that enter your mucosal surfaces, your respiratory tract, your GI tracts, the coronavirus, for example. So starting, you don't even have to go into the trachea and into the lungs. Even it starts right here. So paranasal sinuses, your frontal sinus, your ethmoidal sinus, or the maxillary sinus. All these, you will have sinusitis. Okay, sinusitis, recurrent sinusitis, and those things. So you know the mechanism. CD40 ligand is defective. So TH cells fail to express this functional CD40 ligand. co-stimulatory signal is not received. So, first signal is received, but the second signal required for class switching. What all things is it required for the second signaling? It is required for B cell activation into plasma cells, okay, which will secrete a lot of 2000 molecules per second, like that. So that won't happen. It is required for switching the IgM into IgGAE. That won't happen. It is required for making memory cells. So there will be no memory cells formed. The T independent response, which only relies on antigen antibody interaction, it is weak because it does not make use of T cells. It cannot, it produces only IgM and it never produces memory cells. So here the same thing will happen, no class switching and no memory cells, because the B cell response to T dependent antigens is affected. Now coming to the defects of the innate immune system. So what all are part of innate immune system? There are cells and there are molecules. Cells like neutrophils, macrophages, also dendritic cells, mast cells, basophils. Molecules like the complement. There are other molecules like C-reactive protein, mannose binding, lectin. So they also play a part. Okay, even lysozymes and all. But we'll be concerning ourselves with the phagocytes for now. So there is a leukocyte adhesion deficiency. That means the cells are unable to reach the site of inflammation. They are unable to migrate. How? See, normally the cells flowing through the blood. So this is the site of inflammation outside the vascular compartment. This is the vascular compartment. This is blood, artery, vein, whatever, or capillary. Okay, and this is your tissue. So the cells यहाँ flow होते जा रहे हैं. अब यहाँ पे tissue में कुछ inflammatory stimuli generate हुए. They will secrete some cytokines. So this is your innate immune response. Innate immune response, toll-like receptors से recognize हुआ. उन्होंने कुछ NF-kappa B signaling के through adhesion molecules. So यहाँ पे they start expressing, this endothelial cells start expressing adhesion molecules. So जो cells flow होके fast निकल जा रहे थे वहाँ से, they start slowing down क्योंकि चिपक यहाँ road block. You have seen those Hollywood things, और US में जो करते हैं कि metallic spikes निकाल देंगे. अगर गाड़ी फास्ट जा रही है, रुक नहीं रही है, पुलिस इज ट्राइंग टू स्टॉप दैट, मेटालिक स्पाइक खड़ा कर देंगे, तो टायर पंक्चर हो जाता है गाड़ी का, गाड़ी स्लो होती है फिर रुक जाती है. तो हियर आल्सो इट स्टार्ट्स, फर्स्ट इट टेथर्स, देन इट स्टार्ट्स स्लोइंग डाउन, सो इट स्टार्ट्स रोलिंग. यहाँ तो फ्लो होके फास्ट जा रहा था, उसके बाद रोल होने लगता है, यहाँ फाइनली रुक जाता है स्टेप, फिर वो एडेशन होता है, फिर वो डायापेडेसिस मतलब यहाँ से वहाँ शिफ्ट करता है सेल के शेप को, एंड ट्रांसमाइग्रेशन अक्रॉस द गैप. So because of the innate immune response, the endothelium has started separating from each other. Gaps बढ़ जाते हैं. Not only do they express adhesion molecules, they also contract a little so that the interendothelial gaps increase, through which this can easily slip and come out into the tissue. But now ये सब कुछ नहीं हो रहा है. So there is a defect in cell adhesion and migration. It limits the recruitment of cells to the site of inflammation. So cell surface molecules of the integrin. So normally it is the integrin family. I should have highlighted it. Red में समझ लो इसको. इंटीग्रिन फैमिली ऑफ प्रोटीन्स का डिफेक्ट है यहाँ पे. तो ल्यूकोसाइड एडिशन डेफिशिएंसी में, सो देयर आर इंटीग्रिन फैमिली प्रोटीन्स लाइक LFA, MAC, LFA1, MAC1, ऑल दोस. तो वो नहीं एक्सप्रेस हो रहा है. ओके, दे आर एक्सप्रेस्ड हियर. I'm sorry. So they are expressed here on the endothelial surface, and their receptors are expressed on the leukocyte surface. So that interaction fails to happen. Because of that, there is susceptibility to infections. Which ones? I told you, phagocytic defect causes susceptibility to bacteria and fungi. Viruses नहीं करता है because viruses को CD8 cell मारता है using MHC1. It does not need antigen presenting cell. But antigen presenting cell जहाँ चाहिए होता है for CD4 helper cells, so that will be affected. So all bacteria, gram positive, gram negative, fungi. So you can see कि ये एक चाइल्ड है, एक्चुअली नजर नहीं आ रहा तुमको, छोटा बच्चा है, ये बटक्स है उसके. Okay, यहाँ से हमने जनरली posterior superior iliac spine is the site where the bone marrow tap is done. तो इसका bone marrow लिया था उन्होंने, कुछ कारण से लिया होगा, इसी वजह से लिया होगा शायद, इन्फेक्शन चेक करने के लिए कि why is the infection happening. Basically they must have seen a low leukocyte count, so they are trying to find whether bone marrow में बन रहा है कि नहीं. So they took a tap bone marrow aspiration, they did, but that site got infected. So normally it should not get infected. It has gotten infected, you can see here. Similarly here, simply an intramuscular injection was given. Okay, so intramuscular injection to protect against various, like the triple vaccine, diphtheria, pertussis, tetanus, DPT, जो 6, 10 और 14 weeks में मिलता है. So it is given here in the anterior quadriceps. So you can see an abscess has formed. Normally it should not do anything, तुरंत ठीक हो जाना चाहिए, but नहीं हो रहा है. Tonsillitis or umbilicus में infection. So all these things can happen. Chronic granulomatous disease में the lymphagocytes are reaching all right. सब adhesion हो गया, migrate हो गया, पहुंच गए. In fact, they also phagocytosed. So phagocyte मतलब endocytosis कर लिया. Okay, phagocytosis, when we say phagocytosis has two parts. Phagocytosis includes the killing also. So if you learn phagocytosis in detail, you will find that endocytosis is just one part of phagocytosis. It also includes fusion of that endosome with the lysosome, and finally, or through other means, the killing of the ingested material. So that is also part of the phagocytosis. When this neutrophil or macrophage phagocytose, they do both the things. They consume it and they digest it. So that digestion is also part of phagocytosis. So here consumption is happening, but digestion is not happening. So there is a defect in the phagocytic function of neutrophils and macrophages. What sort of defect? NADPH oxidase. So this is one of the NADPH requiring systems. If you go back to your HMP shunt, you will remember there were a few things we had discussed where all HMP shunt plays an important role. So NADPH is required for maintaining RBC integrity. Maintaining RBC integrity through the superoxide NADPH dependent superoxide dismutase, because reduced glutathione is to be made available. That oxidized glutathione gets converted to reduced using your NADPH reductase. So that is not happening. Similarly, NADPH is important for fatty acid biosynthesis, cholesterol biosynthesis, and it is important for this also. So one of the functions is that NADPH oxidase is important for killing. So oxygen gets converted through superoxide radicals like O2 minus and other reactive compounds. So like hypochloric acid, hypochlorous acid, all those things. So oxygen getting converted to what are free radicals? The free radicals are a species produced due to partial reduction of oxygen. So oxygen when completely reduced becomes water, but if it stops in between, it becomes free radicals like superoxide. So this process can happen normally also, where we actually use superoxide dismutase, which is also NADPH dependent, to convert superoxide to water, not to this to water. Okay, we want to convert it to water. So normally that happens, but that is a byproduct of metabolism. That is an unwanted free radical. Here we are talking of a phagocytic cell which is producing superoxide deliberately to kill the bacteria. Okay, so this is happening in a very मतलब observed jail के अंदर कर रहा है वो, ऐसा नहीं कि पूरे सेल को अफेक्ट करने वाला. This superoxide is generated inside your endosome, okay, inside your lysosome, inside your phagosome basically. Oxygen is converted to superoxide. This is basically you're trapping something. It's a very cruel analogy, but that is what the cell is doing. So it is, किसी को पकड़ा है, उसको एक जेल में बंद किया और अब वहां पे टॉर्चर के वेपन्स लेके जा रहा है, तो सब तलवार भाला whatever. So it's very gruesome, but that is what the cell is trying to do. Inside the phagosome, it is generating superoxide. Through superoxide, it is generating hydrogen peroxide, other reactive oxygen species like hypochlorous acid and all, and it is going to attack that particular cell and going to kill it. So this is you can see here. So this is the cytosol. यहाँ पे कुछ नहीं हो रहा है, अपने आप को कुछ नहीं करेगा, but inside the jail, inside the phagosome, outside the cell, inside the phagosome, it is going to kill them. But now, if this NADPH oxidase is defective, I have not the defect, so that defect is known as the FOX gene or other gene. So if that is defective, then the killing won't happen. So you will phagocytose, consume to karoge, but kill nahi karoge. So that will, those bacteria, those microbes will survive. So again, phagocytes कौन से infection कराएगा? Bacteria, fungus, recurrent bacterial, recurrent fungal infections. So you have, enlarged lymph nodes मिलेगा, lungs में pneumonia, liver abscess, stomach में granuloma. So excessive inflammatory responses, basically the cells are coming, they are unable to kill, more cells are coming, more inflammatory response, more consumption is happening, digestion is not happening. All that leads to formation of granulomas. So granulomas are a particular pathological entity. You will learn about them in your pathology class in second year. So basically, you just remember that there are some necrosed material in between, in the center, surrounded by activated macrophages and all. तो मैक्रोफेजेस बहुत सारे जमा हैं, बीच में थोड़ा नेक्रोज मटेरियल है, ऑल दैट इज नोन एज अ ग्रानुलोमा, कॉमनली सीन इन delayed type hypersensitivity responses or in tuberculosis, cell mediated responses जहाँ भी होता है बहुत सारे macrophage जमा हो जाते हैं, so that is known as granuloma. So granulomas will be found in lymph nodes, in your stomach, in your urinary tract, all that. Okay, skin abscesses, infections, granuloma, acne, bone infections. Summary, the same thing, I'm not going to cover it again. You look at the same diagram actually. Stem cell, the common myeloid lymphoid progenitor, the myeloid lymphoid progenitor. In fact, we have, this diagram does not show the myeloid cell. Okay, this only talks about the adaptive immunity, the lymphoid system. यहाँ पे myeloid, common myeloid lymphoid progenitor दिखाया, but they haven't shown your myeloid pathway. They haven't talked about phagocytes. Here they have shown pro-B, meaning B cell precursor, and T cell precursor. T cell precursor has already migrated to the thymus. So B cell precursor, either from pre-B cell, it does not go to the mature B cell. So that heavy chain rearrangement has happened, but the light chain rearrangement is not complete. So IgM has not yet been expressed properly. So यहाँ पे अगर रुक गया तो X-linked A gamma globulin में. Also Bruton's tyrosine kinase defect जो हमने देखा उसमें भी यही होता है. Bruton's tyrosine kinase defect में your signaling, actually some signaling is required from the antigen antibody to produce this particular gene rearrangement. Okay, I mean you don't need those details. So that that is known as X-linked A gamma globulinemia, meaning precursor B cells are not developing into a mature B cell. You will not have no mature B cells in circulation. Second, your mature B cell has formed with IgM and IgD on their surface, and they are getting activated into, so this is an immature getting converted to mature. This is another step they have shown. We didn't discuss this. This is combined variable immunodeficiency. CD40-40 ligand interaction, that is X-linked hyper-IgM syndrome because of CD40 ligand defect. IgA deficiency, selective IgA deficiency because of class switching, some problem in class switching. So these, see, you can see here that the T cell comes, interacts with the B cell, then the class switching into IgG, IgA, IgE happens. Otherwise, it is only IgM. Before the class T cell interaction, it's only IgM. And T cell defects. Now, T cell defects mostly produce combined immunodeficiencies. ADA deficiency, like I told you, it leads to purine accumulation, adenosine accumulation. DNA synthesis is affected. It affects the T cell. T cell, any T cell defect will affect your class switching. It will affect your memory cell formation. And then X-linked SCID. So SCID, whatever you saw, all those RAG1, RAG2, interleukin 2 receptor defect or whatever. Immature T cell, and then DGeorge syndrome because thymus dysplasia is there. MHC class 2 deficiency, that is the Bayer lymphocyte syndrome. So all those things.